Hello, my name is Ali Gholami. I'm a PhD student in University of Nevada, Reno. I'm also research assistant in Center for Advanced Transportation Education and Research in Department of Civil and Environmental Engineering in University of Nevada, Reno. In this presentation, I provide a method for estimating intersection turning volumes from actuated non-coordinated traffic signal information. The outline of this presentation is as follows. First, a brief introduction about application of turning volume movement volume. Then I describe why this method is proposed here, and the methods are explained, and finally methods are applied on 3 intersections. Turning movement volume has a lot of different applications in transportation engineering. Here you can see a few examples. In intersection operational analysis, traffic safety, or travel demand, and so on. IT in this report explains that if loop detectors be configured and placed properly, they can produce excellent counts. However, in the current practice in Reno and Sparks shows that these loop detectors are not configured properly. So the error in many cases is even more than 70%. For example, here you can see that it is more than 70%. So we have 2 options to get turning volumes: either manually, that is expensive, time assuming, and not continuous, or automatically using loops that the accuracy is very low. So we proposed another method that you can get counts from traffic signal information, that it's easy to implement. So in this presentation we show how. The proposed methodology here is that first we can get signal data from central computer, and then at the same time we collect manual counts for a pilot period, and then we model the intersection in vSIM for changing the volumes, different volumes. Instead of doing it manually in vSIM, we can use a COM interface, that is a vSIM tool. Then based on the data that we can get from vSIM, we can make a prediction model for data. And finally, we can use and calculate mean absolute percentage error to see that our model is acceptable for future use or not. Here is a sample of signal information that I got from City of Reno. You can see that each cycle, it shows each cycle and each phase, that how much it takes to be turned to another phase. Simulation, as I said, was done in vSIM using the COM interface. So we modeled our intersection in vSIM and changed our volumes in COM. For making the models, we use regression and genetic programming. In regression, user must specify the structure of the model, that sometimes it is not easy. But in genetic programming, GPU automatically evolves both the structure and the parameters. Here is an example to show that how GPU works. Here we have 3 sets of data, X, Y, Z. You can see the relationship between each of these sets with another one. It is not easy to understand that what is the structure of this data. But in fact, it is a data that we got from different triangles. So we are looking to find the Pythagorean theorem. In regular regression, it is not easy to find that equation, but in GP in a few minutes you can get this equation, that if you delete these three last terms that are almost zero, you can get exactly the same Pythagorean theorem. GP uses evolution process, I mean crossover, mutation, and other operators that usually you can see in evolution. It is a little bit difficult to program that process, but you can use ready applications. I use the GP tips that is free and you can download it from internet, and it is easy almost to use it. Also, R is capable of doing GP analysis. Also, you can use a regular regression in R. R is also free, and you can install a lot of different packages, and with installing these packages you can do a lot of different analysis. Based on simulation, we prepared our data that in each cycle shows that how much we have green time and volume that per that cycle, and hourly volume in our major street and our side street. But we don't have these two parameters, so instead of using exactly the volume, we use numbers from 1 to 5, 1 showing the less traffic and 5 showing the highest volume that can happen in that street. And this hourly volume is our dependent variable, and other parameters can be used for independent variables. Here you can see our models and their accuracy in terms of R squared, that you can see in some models it can be very high, and in sometimes that the volume is very low, and accuracy also reduced. For example, here in low volume and very low volume in a major street, you see that R square is not acceptable. But when volume increase, the accuracy also increase. So here you can see the summary of results that show that in all times or side street has a very good accuracy, but when volume is low, you can see that still side street has good accuracy, but major street does not. This is because side street gap out when there is no volume, so always you can predict how much vehicle has passed from that cycle. But when volume is very low, major street signal keep green, so you cannot say exactly how much vehicle are passing from this cycle. Thank you for watching this video.